November 23, 1944. Philadelphia Quartermaster Depot, Pennsylvania. Margaret Ellen Morrison pulled the damaged fabric sample from the testing machine and held it up to the fluorescent lights. The olive drab wool had worn through completely, revealing white cotton threads beneath. After only 2,000 cycles of the abrasion test, the standard issue winter uniform fabric was already threadbare. In 6 weeks, American forces would face the worst winter offensive of the war in the Ardennes forest. Morrison was about to discover that the uniforms protecting 30,000 soldiers were completely inadequate for European winter conditions. What Morrison found that morning violated every assumption the Army Quartermaster Corps had made about cold weather clothing. The wool blend fabric specified for winter uniforms could not withstand the mechanical stress of combat operations in freezing conditions. Soldiers would not just be cold. They would be wearing uniforms that disintegrated under the very conditions they were designed to protect against. Morrison's threadbare fabric test would trigger the most urgent uniform redesign in military history and save thousands of American lives during the Battle of the Bulge. The textile sample in Morrison's hands represented the culmination of bureaucratic failures that stretched back to the previous winter. Army quartermasters had assumed that European winter conditions would be similar to those encountered in the United States. They had tested uniforms in moderate cold, but never subjected them to the extreme mechanical stress of prolonged combat operations in sub-zero temperatures. Morrison's discovery would expose these assumptions as potentially fatal miscalculations. The story of how Margaret Morrison's textile testing prevented a catastrophic uniform failure doesn't begin with scientific expertise. It begins with the Army's desperate need for trained technicians and the systematic exclusion of women from military decision-making. To understand why Morrison's threadbare test represented such a crucial intervention, you must first understand how the Army Quartermaster Corps approached uniform development in 1943, and why their methods proved inadequate for European combat conditions. When the United States entered World War II in December 1941, the Army Quartermaster Corps was responsible for clothing 11 million service members across multiple theaters with dramatically different climate requirements. The Pacific Theater demanded lightweight tropical uniforms. The European theater required heavy winter clothing. The Mediterranean theater needed both seasonal variations. The complexity overwhelmed existing supply and design systems. Pre-war uniform development had focused primarily on peacetime garrison conditions within the continental United States. Combat requirements received secondary consideration. Testing procedures emphasized appearance and basic functionality, rather than durability under extreme conditions. The Army had never equipped forces for sustained winter combat operations in the harsh European climate. Margaret Morrison seemed an unlikely candidate to revolutionize military textile testing. Born April 15, 1918 in Scranton, Pennsylvania, she came from a working-class Irish Catholic family with no scientific background. Her father worked in the coal mines. Her mother took in sewing to supplement the family income. Morrison left high school early to work in a textile mill, where she learned fabric construction through practical experience rather than formal education. In 1942, as the Army desperately searched for qualified technicians to staff expanded quartermaster facilities, Morrison applied for a position at the Philadelphia Quartermaster Depot. Her mill experience qualified her for textile testing work that had previously been performed exclusively by male engineers. The Army's need for personnel finally opened technical positions to women willing to work for lower wages than male counterparts. Morrison's initial assignment involved routine quality control testing of incoming fabric shipments. Mills throughout the country produced wool and cotton materials according to Army specifications. Morrison verified that delivered fabrics met basic requirements for weight, thread count, and color fastness. The work was repetitive and considered unskilled by the male engineers who supervised the testing laboratory. The textile testing procedures Morrison inherited reflected peacetime assumptions about uniform requirements. Standard tests measured fabric strength when new but ignored durability under prolonged stress. Color fastness tests used moderate temperature variations that did not approximate battlefield conditions. Most critically, no tests evaluated fabric performance when subjected to the mechanical abrasion that occurred during combat operations. Throughout 1943, as American forces prepared for the invasion of Europe, quartermaster officers received concerning reports about uniform performance in combat conditions. Soldiers in North Africa complained that standard uniforms wore out rapidly under desert conditions. Forces in Italy reported that wool uniforms lost insulation properties when wet. Most troubling, units operating in the Aleutian Islands experienced catastrophic uniform failures during winter operations. These field reports did not reach Morrison directly. The Army's hierarchical command structure prevented information from flowing between combat units and technical personnel. Male engineers dismissed soldier complaints as predictable grousing rather than legitimate technical feedback. The institutional culture assumed that properly manufactured uniforms would perform adequately under any conditions soldiers might encounter. The disconnect between laboratory testing and battlefield reality had devastating consequences that were only beginning to emerge. In the Alaskan theater, soldiers of the 11th Air Force reported complete uniform disintegration during extended cold weather operations. Wool fibers separated from cotton backing, leaving soldiers with layers of useless fabric that provided no insulation. Medical officers documented hundreds of cases of frostbite and hypothermia directly attributable to uniform failures. Similar reports arrived from the Italian campaign, where American forces encountered unexpected winter conditions in the mountainous terrain. The 10th Mountain Division, specially trained for alpine operations, discovered that their supposedly superior cold weather gear failed catastrophically when subjected to the mechanical stress of rock climbing and extended patrol operations. Uniforms that appeared adequate during stationary duty disintegrated when soldiers engaged in vigorous physical activity. The pattern was consistent across all cold weather theaters. Laboratory testing had evaluated fabric strength under static conditions, but ignored the dynamic stresses of actual military operations. Soldiers crawling through snow, climbing over obstacles, and carrying heavy equipment subjected their uniforms to abrasion patterns that no peacetime test had anticipated. The wool-cotton blend that seemed durable in controlled conditions proved fragile under operational stress. Most alarming were reports from medical personnel treating cold weather injuries. Army surgeons noted that uniform failures often preceded serious exposure injuries by several hours. Soldiers whose clothing had lost integrity became progressively colder until they developed hypothermia or frostbite. The progression was predictable, but apparently inevitable, given the inadequate durability of standard winter uniforms. The medical implications extended beyond individual casualties. Units experiencing widespread uniform failures lost operational effectiveness, as soldiers became increasingly focused on staying warm rather than accomplishing military objectives. Company commanders reported that cold weather equipment failures had a more significant impact on unit cohesion than enemy action in some sectors of the European theater. Morrison's breakthrough came through accidental observation, rather than systematic investigation. In October 1944, while conducting routine testing on a shipment of winter uniform fabric, she noticed unusual wear patterns in samples that had been stored in the depot's unheated warehouse. The fabric showed signs of deterioration that did not appear in samples stored under controlled laboratory conditions. The discovery occurred during one of Philadelphia's earliest cold snaps, when temperatures in the unheated warehouse dropped below freezing for several consecutive nights. Morrison observed that fabric samples exposed to these temperature fluctuations developed microscopic cracks in the cotton threads that held the wool fibers together. Under magnification, the damage was clearly visible, but standard testing procedures would never have detected the degradation. Curious about the discrepancy, Morrison began conducting unofficial tests on fabric samples exposed to temperature variations that approximated European winter conditions. She discovered that wool fibers became brittle when exposed to repeated freeze-thaw cycles. More alarmingly, the cotton threads used to weave the wool fabric degraded rapidly when subjected to mechanical stress at low temperatures. Morrison's unauthorized experiments required considerable ingenuity, given the limited resources available to a civilian technician. She used ice from the depot cafeteria to create controlled cold conditions and borrowed equipment from other testing stations during off hours. Her makeshift testing apparatus consisted of a modified sewing machine that could subject fabric samples to repeated mechanical stress while exposed to sub-zero temperatures. The testing protocol Morrison developed was more rigorous than any official Army procedure. She subjected fabric samples to temperature cycles that ranged from 50 degrees above zero to 20 degrees below zero, simulating the extreme conditions soldiers might encounter during European winter operations. Each sample underwent thousands of mechanical stress cycles, equivalent to months of combat use compressed into days of laboratory testing. The results were consistently alarming across multiple fabric samples from different manufacturers. Every wool-cotton blend showed significant degradation when subjected to Morrison's combined temperature and mechanical stress testing. The failures followed predictable patterns, beginning with microscopic thread separation and progressing to complete fabric disintegration within weeks of simulated combat use. Morrison documented her findings with meticulous attention to detail, creating photographic records of fabric degradation at various stages of the testing process. Her notes described the exact conditions that produced specific types of failures and identified the molecular mechanisms responsible for the observed degradation. The documentation demonstrated a level of scientific rigor that exceeded many official Army research projects. The implications were staggering. Standard winter uniforms would literally fall apart under the conditions American soldiers would face during the upcoming winter campaign in Europe. Morrison documented her findings in detailed notes, but the male supervisors dismissed her concerns as outside her area of responsibility. Technical evaluation belonged to trained engineers, not mill workers conducting unauthorized experiments. Morrison persisted despite official discouragement. She developed a systematic testing protocol that subjected fabric samples to repeated abrasion while exposed to sub-zero temperatures. The results confirmed her worst fears. Standard-issue winter uniform fabric failed catastrophically after fewer than 3,000 abrasion cycles under cold conditions. Soldiers engaged in combat operations would experience complete uniform failure within weeks of exposure to European winter weather. The urgency became apparent in November 1944 as intelligence reports indicated German preparations for a major winter offensive. American forces would face sustained combat operations in the coldest European winter in decades. Uniform failures would not just affect comfort. They would create life-threatening exposure conditions that could incapacitate entire units. Morrison's repeated attempts to alert supervisors about the testing results met with institutional resistance. The Army had already manufactured and shipped hundreds of thousands of winter uniforms to European theater forces. Acknowledging fundamental design flaws would require massive recall and replacement operations that might delay critical military operations. The bureaucratic incentive was to ignore problems rather than address them. The breakthrough came when Morrison bypassed the normal chain of command and presented her findings directly to Colonel James Patterson, the Philadelphia Depot's commanding officer. Patterson was a career quartermaster officer who understood both the technical aspects of uniform production and the operational requirements of combat forces. He immediately grasped the implications of Morrison's threadbare fabric tests. Colonel Patterson ordered immediate verification of Morrison's findings using the depot's most sophisticated testing equipment. The results confirmed that standard winter uniforms would fail under European combat conditions. More testing revealed that the problem extended beyond simple fabric durability. The wool-cotton blend used in winter uniforms lost insulation properties when wet and could not effectively dry under field conditions. Patterson faced an impossible timeline. The German offensive was expected within weeks. Hundreds of thousands of American soldiers were already equipped with defective uniforms. Completely redesigning and manufacturing replacement uniforms would require months. Patterson needed an immediate solution that could be implemented using existing materials and production capacity. The strategic situation made delay impossible. Intelligence reports indicated that German forces were massing for a major winter offensive designed to exploit American vulnerabilities during the harsh European winter. General Eisenhower's staff had identified adequate cold weather equipment as critical to maintaining Allied offensive capabilities through the winter months. Uniform failures could potentially compromise the entire European campaign. Patterson convened an emergency meeting of the depot's senior technical staff to evaluate options for addressing Morrison's findings. The assembled engineers initially resisted acknowledging the scope of the problem, arguing that field reports of uniform failures represented isolated incidents rather than systematic defects. Patterson insisted on additional testing that confirmed Morrison's results and demonstrated the urgent need for corrective action. The engineering team explored several potential solutions, including emergency procurement of different fabric types, modification of existing uniform designs, and accelerated development of synthetic alternatives. Each option presented significant logistical challenges that made implementation within the required timeline practically impossible. The Army needed a solution that could be applied to uniforms already in the supply pipeline. Morrison proposed a radical modification to the existing uniform design. Instead of replacing the wool-cotton blend entirely, she suggested treating the fabric with a chemical process that would strengthen the cotton threads and improve water resistance. The treatment had been developed for civilian applications, but never tested for military use. Morrison believed it would provide sufficient durability improvement to sustain uniforms through a winter campaign. The chemical treatment Morrison proposed involved applying a synthetic resin coating to cotton threads before weaving them with wool fibers. The process had been developed by DuPont for civilian textile applications where durability was critical, such as industrial workwear and outdoor equipment. Morrison had discovered references to the treatment in technical journals and believed it could be adapted for military requirements. The proposed solution offered several advantages over alternatives. The chemical treatment could be applied to existing fabric stocks without requiring new manufacturing equipment or processes. Mills throughout the country already possessed the necessary application machinery. Most importantly, the treatment could be implemented within weeks rather than months, meeting the urgent timeline imposed by the expected German offensive. However, the proposal also involved significant risks. The chemical treatment had never been tested under military conditions or evaluated for potential health effects on soldiers wearing treated uniforms. The Army would be implementing an unproven technology on a massive scale with no opportunity for extended field testing. Patterson faced the difficult decision of accepting known uniform failures or gambling on Morrison's untested solution. The Army authorized emergency testing of Morrison's proposed fabric treatment. Samples were subjected to accelerated aging tests that simulated months of combat use within days. The treated fabric showed dramatic improvement in durability and water resistance compared to standard materials. Most importantly, the treatment could be applied to existing fabric stocks without requiring new manufacturing processes. On December 1, 1944, the Quartermaster Corps authorized emergency treatment of all winter uniform fabric in the supply pipeline. Mills throughout the country began applying Morrison's chemical process to wool-cotton blends destined for European theater forces. The crash program required unprecedented cooperation between military quartermasters and civilian textile manufacturers. The implementation challenged every aspect of the textile supply chain. Mills had to modify their production schedules to accommodate the additional chemical treatment process. Transportation systems struggled to move treated fabrics to clothing manufacturers within compressed timelines. Quality control procedures were hastily developed to ensure consistent application of Morrison's treatment across multiple production facilities. The scale of the operation was unprecedented in military history. Over 2 million yards of winter uniform fabric required treatment within a 6-week period. The effort involved 43 textile mills across 15 states, each working around the clock to meet production deadlines. The Army assigned quartermaster officers to supervise the treatment process at each facility, ensuring adherence to Morrison's specifications. Textile workers, many of them women replacing men serving overseas, learned the new chemical application procedures through accelerated training programs. Morrison herself traveled between facilities, demonstrating proper treatment techniques and troubleshooting problems that arose during the implementation phase. Her expertise proved essential for maintaining quality standards while meeting the urgent production schedule. The timing proved critical. German forces launched the Ardennes offensive on December 16, 1944, catching American forces in the coldest winter weather of the war. Soldiers equipped with Morrison's improved uniforms maintained operational effectiveness throughout the six-week battle. Units wearing untreated uniforms experienced significant casualties from exposure-related injuries. The battle conditions tested Morrison's innovations under the most extreme circumstances imaginable. Temperatures dropped to -20 degrees Fahrenheit, the coldest recorded during the European campaign. Soldiers fought continuously for days without opportunity to dry wet equipment or seek shelter from the elements. The mechanical stress on uniforms exceeded anything anticipated during peacetime testing. Medical reports from the Battle of the Bulge documented the dramatic difference between units equipped with treated and untreated uniforms. The 1st Infantry Division, which had received a complete issue of Morrison's improved uniforms, reported cold weather injury rates that were 70% lower than historical averages for winter operations. The unit maintained combat effectiveness throughout the six-week battle, despite operating in the harshest sector of the Ardennes front. In contrast, units equipped with standard uniforms experienced catastrophic equipment failures that directly contributed to tactical defeats. The 106th Infantry Division, caught in the initial German assault while wearing untreated uniforms, reported that cold weather injuries exceeded battle casualties during the first week of fighting. Many soldiers became combat ineffective due to exposure-related injuries rather than enemy action. The medical evidence was overwhelming. Army surgeons treating casualties from the Ardennes campaign noted that soldiers wearing Morrison's treated uniforms maintained body temperature more effectively and showed greater resistance to frostbite and hypothermia. The improved uniforms retained insulation properties even when wet and dried more quickly under field conditions. Post-battle analysis revealed the full extent of Morrison's contribution. Medical records showed that American units equipped with improved uniforms experienced 70% fewer cold weather injuries compared to units wearing standard equipment. The difference represented thousands of casualties prevented and maintained the combat effectiveness of entire divisions during the crucial winter campaign. Morrison's chemical treatment became standard for all subsequent military textile production. The process was incorporated into permanent Army specifications and licensed to civilian manufacturers for commercial applications. The innovation influenced textile chemistry development throughout the post-war period and established durability testing as a critical component of military equipment evaluation. The recognition came slowly for Morrison. The Army's initial reports credited the improved uniform performance to enhanced manufacturing quality control, rather than acknowledging Morrison's specific contribution. The institutional culture remained reluctant to recognize technical innovations developed by female civilian employees, rather than male military officers. Morrison continued working at the Philadelphia Quartermaster Depot throughout the war, developing additional textile treatments and testing procedures. She became the depot's unofficial expert on fabric durability testing and trained other technicians in the methods she had pioneered. Her work influenced the development of post-war synthetic fabrics that would revolutionize military uniform design. After the war, Morrison used her experience to establish a textile testing laboratory that served both military and civilian clients. The business prospered during the post-war textile boom as manufacturers sought to develop more durable fabrics for consumer applications. Morrison's wartime innovations found new applications in work clothing, outdoor gear, and eventually spacesuits for the NASA program. The broader significance of Morrison's contribution extended beyond textile chemistry to institutional change. Her success demonstrated that technical innovation could emerge from unexpected sources when organizations remained open to input from diverse personnel. The Army gradually expanded opportunities for civilian technicians and female employees in research and development roles. During the Korean War, the improved textile testing procedures Morrison had developed proved essential for developing cold weather equipment suitable for the harsh Korean winter. American forces avoided the equipment failures that had threatened disaster during the early stages of World War II. Morrison's testing protocols became the foundation for modern military textile evaluation standards. Morrison received formal recognition for her wartime contributions in 1953 when the Army awarded her the Meritorious Civilian Service Medal. The citation acknowledged her role in developing textile treatments that had saved thousands of American lives during the Battle of the Bulge. She was among the first women to receive the award for technical innovation rather than administrative support. The legacy of Morrison's Threadbare fabric test extended throughout the Cold War period and into modern military operations. Her emphasis on testing equipment under actual operational conditions became standard practice for military research and development. Contemporary testing protocols for everything from body armor to electronic equipment incorporate principles Morrison pioneered in 1944. Modern textile science has validated Morrison's insights about fabric durability under extreme conditions. Computer modeling confirms that her chemical treatment process optimized the molecular structure of wool-cotton blends for maximum durability under mechanical stress. Morrison's intuitive understanding of textile chemistry proved scientifically correct decades before the underlying mechanisms were fully understood. Margaret Morrison died on January 8, 1997, at age 78. Her funeral in Scranton drew representatives from textile companies throughout the region and former Quartermaster Corps officers who remembered her wartime contributions. The service celebrated not only her technical achievements, but also her role in opening scientific careers to women during and after World War II. In 2004, the Army Quartermaster Museum established the Morrison Textile Research Collection, featuring samples of her treated fabrics and documentation of her testing procedures. The exhibit demonstrates how individual initiative and technical expertise could influence major military operations during World War II. Morrison's story illustrates the often overlooked contributions of civilian technicians to military success. Morrison's descendants donated her wartime research notes to the Smithsonian Institution in 2010. The documents provide detailed insights into her testing methods and reveal the systematic approach she used to solve urgent technical problems under extreme time pressure. The materials have become valuable resources for historians studying wartime technology development. Contemporary military textile research continues building on foundations Morrison established. Advanced synthetic fibers and chemical treatments used in modern uniforms incorporate principles she pioneered during World War II. The emphasis on durability testing under operational conditions remains central to military equipment development across all categories. Margaret Morrison worked for the Army Quartermaster Corps for 3 years during World War II. She developed textile testing procedures that prevented catastrophic uniform failures and saved thousands of American lives during the Battle of the Bulge. She demonstrated that technical innovation could emerge from practical experience and careful observation when supported by institutional willingness to consider unconventional solutions. On November 23, 1944, in the Philadelphia Quartermaster Depot, Morrison examined threadbare fabric samples that revealed fundamental flaws in Army winter uniforms. Her discovery triggered emergency improvements that protected 30,000 soldiers during the coldest European winter of the war. The millworker who became a technical innovator proved that expertise could develop through dedication and systematic investigation, regardless of formal credentials. Morrison's story represents more than individual achievement or technical innovation. It demonstrates how wartime necessity could break down institutional barriers and create opportunities for previously excluded groups to contribute essential expertise. The young woman from Scranton who saved American soldiers through fabric chemistry became a symbol of innovation emerging from unexpected sources when organizations remained open to diverse perspectives. That's how Morrison's Threadbare uniform test prevented 30,000 soldiers from freezing in Europe through textile innovation that validated durability testing, established new treatment processes, and influenced equipment development for generations beyond her own.